Welcome to the General Relativity lecture series. In this video, I will give some in basic aspects of general relativity. It can be considered as an introduction, but not truly an introduction. I will give some important basic aspects of general relativity. The general relativity is formulated based on some of the facts, like in a freely falling frame, the laws of physics are identical to that of an inertial frame of reference. And the inertial and the gravitational mass are identical. So, based on these facts and a general theory of relativity has been developed by Einstein. So, in relativity, a frame of reference is a four-dimensional coordinate system. And the geometry of space-time does not give a selection to any special class of frames to formulate the laws of physics. So there is no specific frame of reference. So space and time does not give a selection to any special class of frames. And there will be acceleration. The acceleration is same for all masses. So these are some of the basic facts behind the development of general theory of relativity. So Einstein argued that under any kind of motion, the laws of physics should be invariant. And the equivalence of laws in any arbitrary coordinate system leads to the introduction of a gravitational field. So this is the principle of general covariance. And we will see if there is a field, you can define a potential there. So during this video lecture, we will see the nature of that potential and the gravitational field. So based on the principle of general covariance, Einstein tried to generalize the result into arbitrary frames of reference. The laws of physics should be invariant and should remain the same in all frames of reference. So Einstein invoked tensors to explain, and he used the tensor algebra to do the calculations in general relativity, because tensors are invariant quantities and it should remain in all frames of reference. So when we change the coordinates, the tensor will not change. It remains invariant. So what are tensors? Tensors are entities which transform invariantly in all coordinate systems. And we can assign physical significance to each of the tensor quantities. We are having a tensor to define curvature in general relativity. We have a metric tensor, we have Riemann tensor. So to define various physical aspects, we have tensors in GEA. Now this is the time to quote the words of Wheeler. Matter tells the space-time how to curve, and the curved space-time tells the matter how to move. Therefore, gravitational potential and forces have to be identified by geometrical parameters. Now, we can see the basic or the fundamental tensor entity, the metric tensor. The metric tensor G alpha beta is a tensor quantity. The metric tensor is denoted by G alpha beta. It is a tensor quantity in a four-dimensional space-time. The fourth dimension is the time in addition to the three space coordinates. The metric tensor plays the role of a potential for the gravitational field. We know that the first derivative of the potential will represent force. So the derivative of a metric tensor involves Christoffel symbols. Now we can have a similar equation to that of a Poisson equation, and the Poisson equation involves the second derivatives. So in the Poisson equation, when we modify the Poisson equation in GR, in the right hand side you can have the stress energy tensor, which is a second order tensor. So you need to develop a tensor from the potential in the left hand side. So Einstein and Grossman arrived at the Ricci tensor, which they got from contracting the Riemann tensor, and that is the Einstein field equations. So in the Einstein field equation, you have this Ricci tensor in the left hand side, and the term involving the stress energy tensor in the right hand side. It's a tensor equation. It's a second order involving second order tensors, and there are a few number of exact solutions for Einstein field equations. And the exact solutions are Runsian manifold equipped with certain tensor fields. And these tensor fields should give rise to specific contribution to the stress energy tensor. And when all the contributions to the stress energy tensor are added up, the result must satisfy the Einstein field equations. And I am listing a few number of exact solutions of Einstein field equations. The Schwarzschild metric, it's an exact solution for a spherically symmetric fluid. So a star can be considered as a fluid and in the interior, and in the exterior it's a perfect vacuum. So that is represented by a Schwarzschild metric. It's a non-rotating star, spherically symmetric. So that's a perfect fluid solution. Then Reisner-Nordstrom metric. This is also a spherically symmetric solution in which the source can be considered as a point static charge. Now Kerr metric, it is the first exact solution for a source with the angular momentum. The Schwarzschild de Sitter metric, this solution we got after introducing the cosmological constant. So here the exterior is not flat. We can have a space with a constant curvature. So that is the solution in the Schwarzschild de Sitter metric. We have a space with a constant curvature because of the cosmological constant. And Reiner-Nordstrom de Sitter metric, it is similar to that of a static point charge with the cosmological constant. Now, Vaidya metric, this solution was invoked by Indian physicist Prahlad C. Vaidya. So here, the solution is for a non-rotating star. We can explain primordial black holes which emits Hawking radiation with the help of Vaidya metric, because here the mass is varying with time. So such a solution is possible with the Vaidya metric. So here I have listed only a very few exact solutions. There are very few exact solutions. I will discuss that in the next lecture series. Thank you.